May 26th. A 6 billion ton plasma cloud launched 6 days ago is hours away from striking Earth, and the satellite measuring its magnetic field just returned something that has never appeared in 25 years of recorded space weather data. A reading of absolute zero. No polarity, no direction, nothing. What nobody is saying yet, every forecasting model NOAA owns just went completely blind. Stay with me, because in under 24 hours, we'll know whether Earth's already damaged magnetic shield holds against something physics says shouldn't exist, and I'll walk you through exactly what to watch for. Now, let's begin. The Space Weather Prediction Center in Boulder, Colorado runs 24 hours a day, 365 days a year. Most nights, it's quiet. Routine. A skeleton crew monitors the solar wind, logs the numbers, drinks bad coffee. The screens glow steady. The magnetometer feeds scroll at their usual pace. Nothing dramatic. Nothing that makes your stomach drop. May 26th. 2026 was not one of those nights. Somewhere around 3 in the morning, the night shift technician on duty was watching the data stream from OES satellites when the numbers started doing something wrong. Not wrong like a sensor glitch, not wrong like a calibration drift you've seen 100 times before. Wrong in the way that makes a trained scientist push back from their desk and stare. The magnetometer readings were jumping, not spiking in one direction, not crashing to one extreme, just stuttering, flickering between values that made no physical sense in sequence. And then, cutting through all the noise, one number settled onto the screen and stayed there. 0. Not close to 0. Not a weak positive or a faint negative, buried in instrument noise. 0. The interplanetary magnetic field component, known as BEZ, the single most important number in all of space weather forecasting, was reading null. Absolute null. As if the 6 billion ton plasma cloud hurtling toward Earth at 3,000 kilometers per second carried no magnetic field whatsoever. Let's make sure that image lands properly. 3,000 kilometers per second. That is 10,800,000 kilometers per hour. The distance from the Sun to Earth is roughly 149,600,000 kilometers. A typical coronal mass ejection, what scientists call a CME, travels that distance in anywhere from 1 to 3 days, depending on its speed. Fast ones arrive in about 18 hours. The one launched on May 20th took 6 days to reach us, which tells you something immediately. This was not a typical fast CME blasting through clear solar wind. This was a massive, dense, almost architecturally complex structure pushing through the heliosphere at a pace that suggested enormous bulk, enormous momentum, and enormous internal energy. Billions of tons. That is not a metaphor. Coronal mass ejections routinely carry between 1 billion and 10 billion tons of solar plasma, ionized hydrogen and helium, threaded through with magnetic field lines, accelerated to speeds that dwarf anything humans have ever engineered. The one on the screens that morning was on the higher end of that mass estimate, possibly beyond it. A mountain range, liquefied into charged particles, launched from 93 million miles away, aimed directly at the third planet. And it was reading 0 on the magnetic field sensor. The instrument responsible for that reading is the magnetometer aboard DSCO-VR, the Deep Space Climate Observatory, positioned at the Lagrange Point 1, a gravitationally stable location approximately 1,500,000 kilometers sunward of Earth. DSCO-VR sits there like a Coast Guard buoy, measuring everything that passes through on its way to us. Its job is to detect the magnetic orientation of the solar wind before it hits. Specifically, it measures BZ, the north-south component of the interplanetary magnetic field, expressed in units called nanoteslas. That morning, BZ was reading 0 nanoteslas, and alongside it, The helicity measurement, the rotational twist of the magnetic field embedded in the plasma cloud, was returning what physicists call null helicity. No twist, no orientation, no detectable magnetic structure of any kind. Here is why that is not just unusual. Here is why that is, by the established laws of physics, supposed to be impossible. In 1861, James Clerk Maxwell unified electricity and magnetism into a single framework. Building on earlier work by André-Marie Ampère and Michael Faraday, he demonstrated mathematically that moving electric charges generate magnetic fields always, without exception. This is not a tendency. It is not a statistical likelihood. It is a physical law as foundational as gravity. When charged particles move, they create magnetic fields. Full stop. No known physical process allows a stream of charged particles to travel through space without producing a measurable magnetic signature. A coronal mass ejection is, by definition, a stream of charged particles, billions of tons of ionized plasma, moving at 3,000 kilometers per second. According to every principle of classical electromagnetism, principles that have been experimentally verified for over 150 years, that object must have a magnetic field. It must have a BZ value. It must have helicity. The laws do not allow for a null result. The laws have never, in the entire history of observational solar physics, produced a null result for an object of this size and velocity. And yet, the screen said 0. NOAA's Space Weather Prediction Center did not hesitate. There was no internal debate about instrument error, no wait-and-see approach, no cautious escalation through the lower alert levels. They went directly to G5, watch the maximum tier of geomagnetic storm warning, and the operator on duty added a line to the official forecast log that has since been seen by researchers across 3 continents. It was not algorithmic. It was not auto-generated. It was typed by a human being who understood exactly what it meant. All magnetometer models are now invalid. 4 words that effectively said everything we built to protect you from this every predictive model, every early warning algorithm, every forecast tool developed over 25 years of space weather science, none of it applies to what is coming right now. To understand why that single null reading caused that level of response, you need to understand what the world looks like when everything is working normally, when the numbers behave the way physics says they should, and the warning systems function the way they were designed. Every coronal mass ejection that has ever been recorded carried a magnetic field, every single one. This is not cherry-picked data. This is the complete observational record going back through 25 years of continuous satellite monitoring, through the Halloween storms of 2003, through the intense solar activity of solar cycle 23 and 24, through every G4 and G5 event in the modern measurement era. When a CME erupts from the sun's surface, it doesn't just throw out raw plasma. It carries with it a twisted rope of magnetic field lines, a structure physicists call a magnetic flux rope wound, and braided by the violent convective dynamics of the solar corona. Think of it like a spring that has been compressed and then released. The plasma doesn't travel in a straight beam. It spirals, it rotates. It has what scientists call helicity, a measurable, quantifiable degree of magnetic twist, either left-handed or right-handed. That persists all the way from the sun's surface to Earth's doorstep. Embedded within that helical structure is the BZ component, the north-south orientation of the magnetic field at any given moment as the CME passes the DSCO-VR satellite at Lagrange point 1. BZ positive means the field is pointing northward, the same general direction as Earth's own magnetic field at the equatorial plane. When a CME arrives with strong positive BZ, the two fields are aligned. They push against each other like the matching poles of two magnets. Earth's magnetosphere absorbs the pressure, deflects the plasma flow, and the storm that results is moderate at worst. The planet's natural shield holds. BZ negative is where things get dangerous. When the CME's field points southward opposite to Earth's field, something called magnetic reconnection occurs at the boundary of the magnetosphere, a region called the magnetopause. The opposing field lines don't repel, they break. They snap and reconnect in new configurations, like two crossed wires shorting out. This process tears open the magnetosphere's outer layers and allows enormous quantities of solar plasma to funnel directly into near-Earth space, accelerating particles down field lines toward the poles, driving electrical currents through the ionosphere, and inducing ground-level voltage surges in long-conducting structures like power transmission lines. That is a geomagnetic storm. That is what G1 through G5 describes. The stronger the southward BZ, the longer it persists. The more violent the reconnection and the higher the G rating. NOAA's early warning infrastructure is built entirely around this relationship. The DSEO-VR satellite at Lagrange point 1 sits approximately 1,500,000 kilometers from Earth. At typical solar wind speeds of around 400 to 800 kilometers per second. That distance translates to roughly 15 to 60 minutes of advance warning before a CME's magnetic field reaches Earth's magnetosphere. 15 to 60 minutes for power grid operators to prepare, for satellite operators to put spacecraft into safe mode, for airlines to reroute polar flights, for the entire global infrastructure that depends on stable electromagnetic conditions to brace itself. The system works like this. DSCO-VR measures BZ in real time. Those measurements feed into a suite of predictive models, the Wang-Shili-Arg model, the Enlil solar wind model, the EUHFORIA framework, which calculate the expected storm intensity and duration. Based on those outputs, NOAA's forecasters issue alerts at graduated levels G1 for minor, G2 for moderate, up through G5 for extreme. Each level has defined thresholds. Each threshold triggers specific recommended responses from grid operators, aviation authorities, and satellite controllers. The system is not perfect. BZ can shift direction abruptly after the initial reading, turning a predicted G2 into a sudden G4 with almost no warning. That unpredictability is already a known vulnerability. But within that imperfection, the system has a foundational assumption that has never been violated in 25 years of continuous operation. The assumption is that BZ will have a value, not a convenient value, not a safe value, just a value, positive or negative, strong or weak, stable or fluctuating, something the models can ingest, something the algorithms can process, something that obeys Faraday's law of induction and Ampere's force law and the basic electromagnetic physics that underpins every instrument in the network. In 25 years, every CME that crossed Lagrange point 1 produced a measurable BZ, fast ones, slow ones, massive ones, weak ones. All of them had detectable magnetic structure. The record of solar observation going back further than DSCO-VR, through the ACE satellite era, through the IMP-8 mission of the 1970s, shows the same consistency. Charged plasma moves through the heliosphere. Charged plasma generates magnetic fields. BZ is always there. Until May 26, 2026, when the 6 billion ton object moving at 3,000 kilometers per second arrived at Lagrange point 1 and handed the sensors a null. And that null didn't just confuse the models, it didn't produce an uncertain output or a wide confidence interval, it broke them. All magnetometer models are now invalid because every model in the network requires a real BZ input to generate a meaningful forecast. Feed them 0, feed them null, and you don't get a bad prediction. You get no prediction at all. The warning system that the entire planet depends on went effectively blind at the worst possible moment. There is one more piece of context that makes this even harder to absorb. The ionosphere, the electrically charged upper layer of Earth's atmosphere that absorbs and deflects much of the incoming solar energy during a geomagnetic storm, was not in a healthy state going into this event. A G4 storm earlier in May 2026 had already stressed it severely. Recovery from major ionospheric disturbance takes days, sometimes weeks. The ionosphere that the incoming plasma cloud was about to strike was, in the language of atmospheric physicists, already compromised, already torn. The ghost was coming. The shield was broken. And the instruments designed to tell us what kind of hit was incoming were reading 0. So behind that layer of normalcy, what physical mechanism was actually running and what had shattered it completely? Picture a rifle bullet in flight, not just any bullet one fired with a deliberate engineered spin imparted by the rifling grooves cut into the barrel. That spin is not cosmetic. It is the entire reason the bullet flies straight. The gyroscopic rotation stabilizes the projectile, keeps its nose pointed forward, makes its trajectory predictable. A ballistics expert can look at the spin rate, the caliber, the muzzle velocity, and tell you almost exactly where that bullet will hit and what it will do when it gets there. Now picture a bullet with no spin at all, same mass, same velocity, but tumbling, wobbling through the air with no stable orientation, no predictable angle of impact. You know it's coming. You know roughly when, but you have no idea whether it will hit flat, nose first, sideways, and that difference determines everything about the damage it causes. That is the object currently closing on Earth at 3,000 kilometers per second. Every CME ever recorded traveled like a rifled bullet. The magnetic flux rope embedded in the plasma, that helical twisted structure of field lines wound tight during the eruption, gave it orientation. It had spin, in the electromagnetic sense. The field lines rotated with measurable handedness, either left or right, and that rotation produced a stable, readable BZ signature, all the way from the Sun to the DSCO-VR satellite at Lagrange point 1. Forecasters could look at that signature and know this bullet is coming in at this angle, with this polarity. And here is what it will do to the magnetosphere. What is arriving today has no spin, no orientation, no readable angle, null helicity, BZ equals 0. And that absence is not a technical inconvenience. It is a physical breakdown of the most fundamental input the entire warning system depends on. So what actually causes null helicity? Because here is the uncomfortable truth. It is not entirely unknown. It is just extraordinarily rare, and it has never before appeared attached to an object this fast, this massive, and this close to impact. The most plausible physical explanation involves something called a heliospheric current sheet crossing. The heliospheric current sheet is the vast undulating boundary that separates regions of opposite magnetic polarity in the solar wind, the Sun's north magnetic hemisphere, from its south. It stretches across the entire solar system like a warped, spinning dinner plate, rippling outward from the Sun's equatorial region. When a CME erupts and travels outward, it can, under certain conditions, interact with this sheet if the CME's internal magnetic structure aligns with the boundary in just the right, or rather, precisely the wrong way. The opposing field regions on either side of the current sheet can meet inside the ejected plasma cloud and begin canceling each other out. This is not reconnection in the traditional sense. This is field annihilation. Two regions of magnetic flux pointing in exactly opposite directions, occupying the same volume of plasma, their field lines meeting and destroying each other the way matter meets antimatter. What you are left with, in the region where those fields intersected, is a plasma cloud that is still hot, still dense, still moving at 3,000 kilometers per second, but magnetically hollow. A dead zone at its core, or threading through its structure, where the interplanetary magnetic field reads null because, physically, there is nothing left to read. That is, in the most literal sense, a magnetic ghost. Billions of tons of charged matter, moving at speeds that would carry it from New York to Los Angeles in under 2 seconds, carrying no detectable magnetic identity. And that is precisely why the Wang-Shili-Argay model, the Enlil solar wind simulation, and the ionosphere framework all failed this morning. These models are not simple. ionosphere, the European Heliospheric Forecasting Information Asset, runs magnetohydrodynamic simulations of the solar wind that require significant computing infrastructure to execute. Enlil, developed over decades of refinement, models the three-dimensional structure of the heliosphere and propagates CME parameters through it. Both systems, and every other operational space weather forecast tool currently running, share one architectural dependency. They require a real, non-zero BZ input to calculate the probability and intensity of magnetic reconnection at the magnetopause. The reason is straightforward. Magnetic reconnection probability is a function of the angle between the incoming field and Earth's field. Southward BZ means near anti-parallel alignment. High reconnection probability, large storm. Northward BZ means near parallel alignment. Low reconnection probability, small storm. The entire predictive chain from BZ measurement to reconnection probability to storm intensity to alert level is a sequential calculation where BZ is step 1. When BZ equals null, step 1 returns no value, not an uncertain value, not a wide range, no value. Every downstream calculation in the model chain receives an undefined input and produces an undefined output. The system doesn't generate a worst-case scenario forecast. It generates nothing useful at all, which is why the forecaster on duty this morning did not look at a model output and decide to issue G5 watch. There was no model output. The decision was made by a human being, looking at a BZ reading of 0 nanoteslas on an object of this size and velocity, and applying the only rational interpretation available. We cannot predict this. Therefore, we assume the worst. Now consider what happens at the magnetopause when null IMF actually strikes. In a standard geomagnetic storm, the interaction is violent but structured. Southward BZ drives antiparallel field lines into contact at the magnetopause. Reconnection proceeds at a roughly predictable rate, and the energy input into the magnetosphere, while enormous, follows a physical logic that the system has evolved to handle. The magnetosphere compresses, the ring current intensifies, the polar cusps expand, and the storm develops through recognizable phases: sudden commencement, initial phase, main phase, recovery, disturbing, damaging in extremis, but comprehensible. With null IMF, Earth's magnetic field encounters plasma that carries no coherent orientation. The magnetopause doesn't receive a clear antiparallel or parallel field to respond to. Instead, it may encounter chaotic, rapidly fluctuating microscale magnetic structures, remnants of the annihilated field regions, fragments of helicity that weren't fully canceled, turbulent interfaces between adjacent null zones. Earth's field, trying to respond to an incoherent input, may begin oscillating, not the controlled oscillation of normal storm dynamics, but chaotic oscillation, rapid, irregular swings in field orientation across the magnetopause that drive irregular reconnection events in multiple locations simultaneously. The result is not necessarily a stronger storm in the traditional KP index sense. It may be something harder to categorize: a barrage of unpredictable shock pulses propagating through the magnetosphere in rapid, uneven succession, each one driving a burst of particle acceleration, each one inducing a ground-level voltage transient with no warning, no rhythm, no predictable duration, not one large wave you can brace for, dozens of irregular waves arriving at random intervals, hitting infrastructure that was designed to survive one sustained assault, not a prolonged chaotic battering from every angle at once. That is what is coming. That is what the null is. Not the absence of danger, the absence of the information we need to understand the danger. But this is not the first time Earth has faced the sun's rage. History has witnessed catastrophes like this before, and they remind us of just how devastating the real scale of destruction can be. September 1st, 1859. A British astronomer named Richard Carrington was sketching a particularly large cluster of sunspots through his telescope when he observed something no scientist had ever documented before: a sudden, intensely brilliant flash of white light erupting from the sun's surface. So bright it was visible in broad daylight, lasting approximately 5 minutes before fading. He noted the time. He published his observation. And 18 hours later, far faster than any solar event before or since the CME he had watched being born arrived at Earth. What followed was the most powerful geomagnetic storm in recorded human history. Telegraph operators across North America and Europe reported sparks jumping from their equipment. Some systems continued transmitting messages even after operators disconnected the power supply entirely. The induced electrical current from the geomagnetic disturbance was strong enough to run the hardware on its own. Several telegraph offices caught fire. Aurora Borealis was visible as far south as Cuba, Colombia, and Hawaii. In the Rocky Mountains, gold miners reportedly woke in the middle of the night believing it was dawn. The sky was so bright. This was 1859. The global electrical infrastructure at the time consisted almost entirely of telegraph wires. The civilization-level damage was, by modern standards, minimal. Disrupted communications. Some fires, a few weeks of repair work, now run the same event through the infrastructure of 2026. The estimate most cited by risk analysts and insurance actuaries is somewhere between $2 trillion and $20 trillion in direct economic damage. That is not a fringe number. It comes from a study commissioned by the Lloyd's of London Market, a National Academy of Sciences report, and subsequent updates from the Cambridge Center for Risk Studies. The range is wide because the actual damage depends heavily on the storm's duration and the preparedness of grid operators. But even the low-end $2 trillion represents economic disruption on a scale that would take years to absorb. The high end would represent the largest single economic event in recorded human history. The Carrington event was not a mystery. It had a clear southward BZ. The models, had they existed, would have predicted it. The people affected had no warning system, but the physics was comprehensible. Move forward to October 29th through 31st, 2003, the Halloween storms, 2 X-class solar flares in quick succession, producing a pair of fast CMEs that arrived at Earth within hours of each other. NOAA rated the resulting geomagnetic storm at G5. It was, at the time, the strongest storm since the modern monitoring era began. The damage was concrete and measurable. More than 10 satellites were permanently damaged or had their operational lifetimes significantly shortened. The entire southern region of Sweden lost power for approximately 1 hour brief. But a preview. High-frequency radio communication used by aviation across the North Atlantic was disrupted for days, forcing airlines to reroute hundreds of flights away from polar paths. The FAA issued ground stops at several airports. The Martian Radiation Environment Experiment aboard the Mars Odyssey spacecraft was destroyed. Astronauts aboard the International Space Station were ordered to shelter in the most radiation-shielded section of the station for extended periods. That was a standard G5 event. BZ was measurable throughout. It swung southward, hard, and stayed there. The models predicted the intensity with reasonable accuracy. Grid operators had enough warning to implement protective measures in most regions. The damage was significant. It was not catastrophic to civilization. Then came May 10 through 12, 2024, the strongest geomagnetic storm in 20 years, G5 classification, driven by a complex series of CMEs associated with a particularly active sunspot region. The storm produced aurora borealis visible across the continental United States, across Central Europe, and this is the detail that surprised many across parts of Vietnam and Thailand. People in Ho Chi Minh City photographed aurora from their rooftops. In Bangkok, the southern horizon glowed faintly red. These are latitudes where aurora is essentially unheard of under normal conditions. The May 2024 storm was powerful, but it followed the playbook. BZ went strongly negative. The models predicted a major storm. The warning was issued in time. Infrastructure operators responded. There was disruption, GPS errors, radio blackouts, some satellite orbital adjustments, but no grid collapses, no cascading infrastructure failures. The system worked because the system had a number to work with. Every G5 storm in the modern satellite era, every single one, gave forecasters a BZ reading. The May 2024 event gave them a BZ of -31 nanoteslas at its peak. The Halloween 2003 storms gave them sustained southward BZ values throughout the active period. Even the estimated parameters reconstructed for the Carrington event, based on geomagnetic records from ground observatories, suggest a powerful but physically coherent southward field orientation. All of them were predictable in principle. All of them gave the warning system something to work with. Today is different, not because the energy is necessarily larger, though at 3,000 kilometers per second with estimated mass in the billions of tons. It may well be. Today is different because the one piece of information that makes a G5 survivable, the BZ value that tells forecasters what kind of impact to expect, is not there. And the layer of atmosphere that is supposed to absorb part of the blow, it was already damaged going into this. A G4 event in early May 2026 drove sustained ionospheric disturbances that pushed the total electron content measurements into anomalous territory across the northern hemisphere. Full recovery from that level of ionospheric stress takes between 10 and 21 days under normal solar wind conditions. That recovery window had not closed. The ionosphere that was intact and relatively healthy during the Halloween storms of 2003, the ionosphere that managed the May 2024 event without catastrophic structural failure, was not the ionosphere in place this morning. The shield that took all those previous hits at full strength is cracked. And now something is coming that the instruments cannot characterize, the models cannot simulate, and history offers no direct precedent for. An isolated event would already be frightening enough, but the picture turns considerably darker when you look at the entire system operating all at once. The May 20th superflare did not arrive in a vacuum. That is the first thing you need to understand. It did not erupt from a quiet, stable sun into a calm heliosphere and travel 6 days through undisturbed space toward a healthy, well-rested planet. It erupted from a sun that was already running near the top of its activity range into a solar system already saturated with elevated particle flux, toward an Earth whose upper atmosphere was still carrying the bruises from a storm it hadn't finished recovering from. To understand the full weight of what is closing in on us right now, you have to zoom out and look at all of it simultaneously. Solar cycle 25 was, by most early predictions, expected to be a moderate cycle. When it began around December 2019, The consensus forecast from the International Panel of Solar Physicists suggested peak sunspot numbers somewhere around 115 respectable, but not historically extreme. What actually happened confounded those predictions entirely. By mid-2024, the cycle was already tracking significantly above forecast. By 2026, it had surpassed the peak of solar cycle 24 and was approaching territory not seen since solar cycle 19 in the late 1950s, one of the most energetic solar cycles in the modern observational record. What that means in practical terms at solar minimum: X-class flares, the most powerful category in the classification system, occur perhaps a handful of times per year, sometimes less. At the peak of an average cycle, you might see 2 or 3 per month during active periods. At the kind of peak solar cycle 25 has delivered in 2026, X-class events have been occurring at 3 to 4 times the rate typical of solar maximum. Not occasionally, consistently. Week after week, active region after active region rotating across the solar disk and erupting before it rotates out of Earth-facing position. The superflare of May 20th, 2026 did not come from a random, isolated sunspot. It originated from active region designated AR active region with a number above 4,000, a numbering sequence that reflects how many distinct active regions have been cataloged since systematic monitoring began. This particular region had been tracked for days before the eruption. And what the Solar Dynamics Observatory data showed was not a simple bipolar sunspot configuration. It was a delta configuration magnetic field, the most dangerous classification in solar physics. In a delta configuration, regions of opposite magnetic polarity are packed so tightly together, separated by distances sometimes smaller than the sunspots themselves, that the magnetic field lines between them are under extreme stress. They don't coexist stably. They coexist under pressure, like 2 opposing magnets being forced together by an external hand, until something gives. On May 20th, something gave. The classification of that flare came back at the high end of the X-class scale. The exact peak flux was still being refined in the hours after the event, but preliminary readings from GEOES satellite X-ray sensors placed it firmly among the most energetic flares of the cycle, possibly of the last 2 solar cycles combined. The associated CME launched at a speed that initial coronagraph imagery from the Solar and Heliospheric Observatory SOHO and the Stereo spacecraft put at approximately 3,000 kilometers per second. That number was revised slightly in subsequent analysis, but not downward. And this eruption did not happen in isolation within the active region's history. In the days preceding May 20th, the same region had already produced multiple M-class flares and at least 2 moderate CMEs that had propagated outward into the heliosphere ahead of the big one. This matters because those earlier ejections carved a path they pushed through the ambient solar wind, created a slightly evacuated channel, and in doing so, may have altered the conditions through which the May 20th CME was traveling. Some researchers have proposed that precursor CMEs can actually accelerate a following, more massive ejection by reducing the drag environment in front of it. Whether that mechanism contributed to the 6-day travel time rather than a faster arrival is still being analyzed. Meanwhile, the ionosphere above Earth had not been given any time to breathe. A G4 geomagnetic storm in early May 2026, driven by a separate CME from a different active region, had already worked the ionosphere hard. G4 is the second highest classification, 1 level below the maximum. It is the kind of storm that causes widespread radio blackouts, significant GPS positioning errors, and aurora visible at mid-latitudes. That storm's ionospheric effects were not cosmetic. Total electron content measurements, the standard metric for ionospheric density and stability, showed persistent anomalies across the northern hemisphere for more than a week after the storm's main phase ended. High-frequency radio communication used by aviation, maritime operations, and emergency services was intermittently disrupted throughout that period. GPS receivers at higher latitudes were logging position errors well outside normal operational tolerances. Recovery from that level of ionospheric disruption is not a switch that flips back overnight. The ionosphere is a dynamic system. It responds to solar ultraviolet radiation, to particle precipitation, to electric field variations driven by the magnetosphere above it. After a major storm, it can take 10 to 21 days for the plasma density structures to restabilize, for the irregularities that cause signal scintillation to smooth out, for the total electron content to return to background levels appropriate for the season and solar activity. That window had not closed when May 20th arrived. The ionosphere was still, in the technical sense, recovering. And then there is the solar corona itself. The Solar Dynamics Observatory, a NASA spacecraft in geosynchronous orbit that has been imaging the Sun in multiple extreme ultraviolet and X-ray wavelengths continuously since 2010, had been returning data in the weeks before May 20th that was drawing attention in solar physics communities for reasons separate from the active region that eventually erupted. The corona, the Sun's outer atmosphere extending millions of kilometers into space, was displaying filament structures, long, dark threads of dense, cool plasma suspended in the coronal magnetic field of unusual complexity and extent. Filaments are not unusual. Large filaments are not unusual. But the spatial scale and magnetic complexity of what SDO was imaging in late April and early May 2026 were described by researchers at the Lockheed Martin Solar and Astrophysics Laboratory as unlike anything they had cataloged in the current solar cycle. Filaments can erupt. When the magnetic field supporting them destabilizes, they can collapse outward and contribute mass and magnetic complexity to an associated CME or trigger 1 independently. Whether the filament structures observed by SDO directly contributed to the properties of the May 20th CME, including potentially to its anomalous null helicity signature, was being actively investigated even as the plasma cloud itself was still in transit. The Global Monitoring Network had seen enough of this picture developing to shift posture well before May 26th. The European Space Agency's Space Weather Service, operating out of its coordination center, had moved to enhanced monitoring protocols following the early May G4 storm and had not stood them down. The Japan Aerospace Exploration Agency JAXA had its space environment monitoring assets in continuous observation mode. Ground-based magnetometer networks, including the SuperMag global array of over 500 magnetometers distributed across both hemispheres, were logging data at the highest available cadence. Ionospheric monitoring stations from Tromsø in Norway to McMurdo in Antarctica were running continuous soundings. All of these systems, collectively, were doing what they were designed to do: watching, measuring, feeding data into models and archives. But none of them could resolve the central problem that emerged on the morning of May 26th. All the instruments in the world cannot compensate for a BZ reading of 0 nanoteslas on an object this size moving at this speed. Watching more carefully doesn't help when the thing you're watching refuses to give you the number you need. The answer to all of it? Why the Sun is behaving this way? Why this particular CME carries this anomalous signature? Why the conditions have converged in this exact configuration lives much deeper than the surface events. We have to go inside the machine. Most people, when they think about the Sun, think about light and heat, a giant burning sphere 93 million miles away, keeping the planet warm. That mental model is not wrong. Exactly. It is just spectacularly incomplete. The Sun is not just a heat source. It is a magnetic dynamo of almost incomprehensible power, a self-sustaining electromagnetic machine that has been running for approximately 4.6 billion years and shows no signs of stopping. And the violence it periodically directs toward Earth is not random. It is the predictable, if complex, output of a physical system operating according to laws we understand reasonably well, even when the specific details surprise us. The engine at the heart of all of this is called the solar dynamo. Roughly 280,000 kilometers below the sun's visible surface lies a boundary layer that has no direct analog in everyday experience. Above this boundary sits the convection zone, the outer 30% of the sun by radius, where energy transport is dominated by the churning, turbulent rise and fall of plasma cells, hot material rising, cooling, and sinking back down in a pattern not entirely unlike the boiling of water, but operating at scales of hundreds of thousands of kilometers and temperatures of millions of degrees. Below this boundary sits the radiative zone, where energy moves by radiation rather than convection, where the plasma is denser, more uniform, less turbulent. The boundary between these two regions is called the tachocline. It is a thin, sharply defined transition layer, relatively thin by solar standards, meaning perhaps a few tens of thousands of kilometers, and it is, according to the current best models of solar physics, the birthplace of the sun's large-scale magnetic field. The mechanism works through differential rotation. Unlike a solid body, the sun does not rotate as a single unit. The equatorial regions rotate faster than the polar regions. The equator completes a rotation in approximately 25 days, while the poles take closer to 35 days. In the convection zone, this differential rotation pattern is relatively well studied. But at the tachocline, the transition from the convection zone's differential rotation to the more uniform rotation of the radiative zone below creates an enormous velocity shear a layer where adjacent plasma regions are moving at significantly different angular speeds. Magnetic field lines threading through this shear layer get stretched, wound, amplified. A field line that passes from the slower rotating interior into the faster rotating equatorial tachocline gets pulled forward, elongated, wrapped around the sun's interior in the direction of rotation. This process is called the omega effect in dynamo theory, and it converts the sun's initial poloidal magnetic field running roughly north to south along the rotation axis into a toroidal field that wraps around the sun in the east-west direction, parallel to the equator. As the toroidal field builds in strength through repeated winding, it eventually becomes buoyant. A region of intensely concentrated magnetic flux, compressed and amplified by the differential rotation, becomes less dense than its surroundings in a specific thermodynamic sense, and it rises. The flux tube pushes upward through the convection zone, threading through thousands of kilometers of turbulent plasma, deforming as it rises and rotates until it breaches the photosphere, the sun's visible surface, and appears as a pair of sunspots, dark, cool, intensely magnetized. The two spots of a pair represent the two ends of the flux loop breaking through the surface, one end carrying field lines pointing into the sun, the other carrying field lines pointing out. This entire cycle from poloidal field to toroidal field to sunspots to solar maximum takes approximately 11 years to complete. Then the process runs in reverse. The emerged flux ropes interact with the surface differential rotation. Their remnant magnetic field diffuses poleward, and the accumulated flux eventually flips the sun's polar field. The north magnetic pole becomes the south. The south becomes the north, and the cycle begins again. Every 11 years. Reliably. For billions of years. Solar cycle 25 is right now at the top of that cycle. The toroidal field wound up over the last 11 years is at its maximum accumulated stress. Active regions are erupting from it at the highest rate of the cycle. The corona is threaded with complex, strained field structures. And within that environment, the May 20th active region with its delta configuration field, its opposite polarity regions jammed against each other under enormous magnetic pressure, was essentially a compressed spring waiting for the last bit of stabilizing tension to fail. When it failed, it launched the complex multi-component CME that is now 6 days into its journey toward us. The Null helicity anomaly almost certainly traces back to what happens when a CME is not a single, clean flux rope eruption, but rather a compound event, multiple eruptions, potentially from the same active region or adjacent regions, firing in such rapid succession that their plasma and magnetic structures are still interacting with each other during transit. In the active region environment of solar cycle 25 peak activity, compound CMEs are more likely than they would be during quieter phases of the cycle. When two flux ropes with opposite helicity, one left-handed, one right-handed, merge or overlap in the heliosphere, their field components can partially or fully cancel in the interaction region. The process is called flux rope reconnection in interplanetary space, and its output, in the region where the reconnection occurs, can be precisely what the sensors measured this morning: null helicity, null BZ, a magnetic dead zone traveling inside a high-speed plasma cloud. Now layer the velocity on top of that. 3,000 kilometers per second is not simply a faster version of an ordinary CME. At that speed, the CME drives a powerful bow shock, a sharp boundary of compressed plasma and magnetic field ahead of it, like the pressure wave in front of a supersonic aircraft, but propagating through the solar wind rather than air. This bow shock arrives before the CME's main body. It compresses the magnetosphere. It drives its own initial disturbance, a sudden commencement signature, recorded by ground magnetometers as a sharp, rapid increase in the horizontal component of Earth's field as the compressed solar wind pushes the magnetopause inward. In a normal storm, that sudden commencement is followed within minutes to hours by the southward turning of BZ, the moment forecasters have been watching for. The moment the interplanetary magnetic field flips southward and reconnection begins driving the main phase of the storm. Operators know this sequence. They use the time between sudden commencement and southward turning to implement final protective measures. With null IMF, there is no southward turning to watch for. There is no moment of BZ going from 0 to negative that signals the onset of major reconnection. The bow shock arrives, the magnetosphere compresses, and then the null arrives. The magnetosphere is suddenly pressed hard against an incoming field that is not coherently pointing in any direction. Rather than a single decisive reconnection event at the nose of the magnetopause, the interaction may produce what some magnetospheric physicists have described theoretically as stochastic reconnection random. Spatially distributed, temporally irregular reconnection events scattered across the magnetopause wherever local field conditions happen to momentarily favor anti-parallel alignment. Not one controlled break in the shield, many small unpredictable breaks, opening and closing in rapid succession across a wide area, each injecting a burst of energy into the magnetosphere, each potentially driving a sharp transient in the ring current, each generating an impulsive voltage change that propagates down to the ground level through field-aligned currents. That is not a storm you can brace for at a specific moment. That is a siege. And the most worrying thing is not a single event. It is when the systems start synchronizing with each other, crossing thresholds we have never had to confront before. There is a concept in engineering called cascading failure. It describes what happens when a system under stress does not simply degrade. It degrades in a way that transfers additional load onto adjacent systems, which then degrade further, which transfers load to the next system, and so on down the chain until what began as a localized problem becomes a civilization-scale event. Engineers design against it. redundancy, circuit breakers, isolation protocols. All of it exists to interrupt the cascade before it propagates. What is about to hit Earth does not care about redundancy protocols. Start with the ionosphere, because that is where the damage is already visible before the May 20th CME has even arrived. The total electron content. The standard integrated measurement of free electron density in a vertical column through the ionosphere, expressed in units called TECU, or total electron content units, had not returned to normal background values following the G4 storm of early May 2026. On a typical quiet day at solar maximum, total electron content values over mid-latitude regions run somewhere between 20 and 80 TECU, depending on local time and season. During the main phase of the early May storm, measurements at several ionospheric monitoring stations across North America and Europe spiked well above 150 TECU before collapsing into a post-storm depression, an equally disruptive condition where the plasma density drops far below normal, leaving the ionosphere thin, irregular, and electrically unpredictable. That post-storm depression had not fully resolved. As of May 25th, 2026, total electron content maps over the Northern Hemisphere were still showing spatial gradients, sharp boundaries between high and low density regions that had no business being there under quiet conditions. These gradients are where signal scintillation is worst. They are the ionospheric equivalent of looking through a glass of water with air bubbles in it. The signal gets there, but distorted, bent, delayed in ways that accumulate into positional errors. Into this already compromised ionosphere, a null IMFCME at 3,000 kilometers per second is about to inject an enormous pulse of energy. The GPS constellation, 24 to 31 operational satellites in medium Earth, orbit at approximately 20,200 kilometers altitude, does not transmit positioning information directly. It transmits precise timing signals. Your receiver calculates its position by measuring the arrival time differences of signals from multiple satellites simultaneously. The entire architecture depends on knowing, with nanosecond precision, how long the signal took to travel from satellite to receiver, and the dominant source of timing error under disturbed conditions is the ionosphere. Signals passing through the ionosphere travel slightly slower than they would in vacuum. The amount of slowdown is proportional to the electron density along the path, which is exactly what total electron content measures. Under stable ionospheric conditions, this delay is predictable enough that receivers can correct for it using standard models. Under severe storm conditions, the electron density becomes spatially irregular and temporally volatile, changing faster than the correction models can track. The result is positioning errors that can reach tens of meters under sustained G5 conditions, with complete signal loss possible at higher latitudes where the storm effects are most intense. Tens of meters. That number means different things in different contexts. For a delivery driver, it is an inconvenience. For an aircraft executing an instrument approach in low visibility, it is the difference between the runway centerline and the runway edge. For a container ship navigating a narrow channel, it is the difference between the channel and the rocks beside it. For precision, agriculture equipment running autonomous operations, for survey-grade construction machinery, for the timing synchronization that underpins cellular networks and financial transaction systems. GPS timing errors of even a few nanoseconds can propagate into service disruptions that have nothing visibly to do with space weather. Under null IMF plus G5 conditions, with a pre-damaged ionosphere, the GPS vulnerability is not theoretical. It is the first domino. The second domino is embedded in the ground under every major city in the industrialized world. Geomagnetically induced currents, GIC, are a direct consequence of the rapidly changing magnetic field that accompanies a severe geomagnetic storm. By Faraday's law of induction, the same foundational physics that makes electrical generators work a changing magnetic field through a conducting loop induces a voltage. Earth's surface, threaded with long conducting structures like high-voltage transmission lines, gas pipelines, and railway tracks, constitutes an enormous network of exactly such loops. When the geomagnetic field changes rapidly and by large amounts, it drives real electrical current through these conducting paths, current that the infrastructure was never designed to carry. In March 1989, a geomagnetic storm rated at what would today be classified as G5 caused a GIC event that tripped the entire Hydro-Quebec power transmission system in approximately 90 seconds. 9 million people in Quebec lost power. The outage lasted up to 9 hours for some areas. Across the northeastern United States, power companies reported transformer damage and abnormal relay behavior. The storm's southward BZ was strong, but not record-breaking, perhaps -25 to -30 nanoteslas at its peak. The event lasted several hours at storm intensity. The conditions approaching on May 26, 2026 could produce GIC amplitudes in long transmission lines that exceed the Quebec event, for the simple reason that the energy input mechanism, stochastic reconnection, driven by Null IMF, may sustain elevated activity longer and with less predictability than the clean single-phase reconnection that drove the 1989 storm. GIC magnitude in a transmission line is a function of the rate of change of the geomagnetic field, not just its absolute value. Rapid, irregular, unpredictable fluctuations, exactly what chaotic reconnection produces, can drive higher peak GIC than a smoother, larger amplitude variation. High-voltage transformers are not fused against GEIC. They are designed to carry alternating current at 50 or 60 cycles per second. GIC is quasi-DC. It flows at near zero frequency, essentially a steady offset on top of the alternating current. When a large GIC flows through a transformer core, it drives the core into magnetic saturation during 1/2 of each alternating current cycle. A saturated transformer draws enormously elevated magnetizing current, generates intense localized heating in the core and windings, and may fail within minutes if the GIC is sustained. The failure mode is thermal. It is irreversible. You do not reset a thermally destroyed transformer by flipping a breaker. Now consider the satellite environment simultaneously. The upper atmosphere, specifically the thermosphere, extending from roughly 80 kilometers to approximately 500 kilometers altitude, which is exactly where most low Earth orbit satellites operate, responds to geomagnetic storm energy input by expanding, heating by particle precipitation, and joule heating from intensified ionospheric currents causes the thermosphere to swell outward. The density at any given altitude increases. For a satellite in low Earth orbit, say, at 550 kilometers altitude, where the bulk of the Starlink constellation operates, increased atmospheric density means increased aerodynamic drag. More drag means energy loss. Energy loss from drag means orbital decay. The satellite slowly spirals inward. Under quiet conditions, this is managed by periodic orbit-raising maneuvers using onboard propulsion. Under severe storm conditions, the density increase can be large enough and abrupt enough that the orbital decay rate during the storm period itself becomes significant. After the May 2024 G5 storm, SpaceX reported that dozens of Starlink satellites required unplanned orbital maintenance. The early May 2026 G4 storm produced similar effects. What a sustained G5 event with chaotic reconnection dynamics will do to the thermospheric density profile over 6 or more hours is, at this moment, unmodeled because the input forcing function, the Null IMF, cannot be simulated with existing tools? There are currently more than 6,000 active satellites in low Earth orbit. Starlink alone accounts for over 5,000 of them. OneWeb, Amazon Kuiper, various national and commercial constellations make up the rest. These are not independent objects with infinite maneuvering capacity. They share orbital altitude bands. Their conjunction avoidance, the process of adjusting orbits to prevent collisions, depends on accurate orbital element updates. If hundreds or thousands of satellites simultaneously experience anomalous drag during a major storm, the uncertainty in their actual versus predicted positions grows faster than the conjunction avoidance process can handle. That is not a theoretical concern. It is a documented operational risk that the satellite industry has been aware of for years and has not solved. And then there is the duration problem. A single G5 peak lasting 1 to 2 hours is damaging. The systems stressed during that window begin recovering as soon as the storm intensity drops. Transformers that did not quite reach thermal failure get a chance to cool. Satellites that experienced elevated drag can be assessed and adjusted. Ionospheric irregularities begin smoothing out once the particle input decreases. A G5 sustained for more than 6 hours does not simply do 3 times the damage of a 2-hour G5. The relationship is nonlinear. Transformers that survived the first 2 hours have been heating progressively. Their insulation has been degrading under thermal stress. By hour 4, some that would have survived a shorter event are approaching failure thresholds. By hour 6, the cumulative thermal damage may push systems over the edge that the initial peak alone would not have reached. The grid does not get a recovery interval between pulses. It absorbs each successive wave from a progressively weakened baseline. That is where the threshold mathematics becomes genuinely frightening, not in the peak. In the accumulation, and while nature is piling up its assault, the defensive wall humanity has built over decades is quietly getting thinner with every passing hour. Here is a number that should be part of every conversation about space weather risk, and almost never is 12 to 18 months. That is the lead time required to order, manufacture, and deliver a large high-voltage transformer, the kind that forms the backbone of national power transmission systems. Not the distribution transformers you see on neighborhood utility poles. The large high-voltage units that sit in major transmission substations, each one weighing between 100 and 400 tons, each one custom-engineered to specification for its specific voltage class and installation site, each one built by a small number of specialized manufacturers, globally primarily in Germany, South Korea, and the United States, whose combined production capacity is measured in dozens of units per year, not hundreds. The United States currently has approximately 2,000 large high-voltage transformers in service. They were not all built recently. A significant fraction of the North American transformer fleet was installed in the 1970s and 1980s, when the design standards for power system equipment did not include geomagnetically induced current as a specified loading condition. It was not an oversight in the malicious sense the scientific understanding of GIC risk to modern power infrastructure was not well developed until after the Quebec event of 1989, and the regulatory update cycle for infrastructure of this age is measured in decades, not years. What this means in practice, much of the transformer fleet, now carrying power to hundreds of millions of people, was designed and built before engineers understood that sustained negative BZ and strong GIC could drive those transformers into the failure modes described earlier. The retrofit programs that have been implemented since neutral blocking devices, GIC monitoring systems, operational protocols for storm conditions are real and have improved the resilience of the most critical nodes. But coverage is incomplete, and the fundamental physics of thermal failure has not changed. If a severe geomagnetic event destroys even a small number of the largest, most critical transmission transformers, the ones moving power across state or national boundaries, the ones that interconnect regional grids, the recovery timeline is not measured in days. It is measured in months to years because you cannot order replacement units off a shelf. You commission them. You wait for manufacturing capacity. You wait for shipping. You wait for installation. Every day that the replacement is not in place is another day that the downstream communities it served have no grid-scale power. This is not a fringe scenario. It was assessed in detail in a 2012 report by Oak Ridge National Laboratory, updated in subsequent analyses by the Federal Energy Regulatory Commission, and repeatedly flagged by the National Academy of Sciences as one of the highest impact, lowest probability risks to national infrastructure. The awareness exists at the institutional level. The vulnerability in the transformer fleet's age and GIC design margins has not been fully resolved. And the warning system that is supposed to give grid operators time to implement protective measures, it is, as of this morning, not functioning. The Wang-Shili-Arge model, the primary operational solar wind forecasting tool used by NOAA's Space Weather Prediction Center, requires real BZ input from the DSCO-VER satellite at Lagrange Point 1 to generate actionable storm forecasts. EUHFORIA. The European operational model has the same dependency. The Enlil solar wind model, despite its three-dimensional heliospheric simulation architecture, produces meaningless output when its BZ input is null. These are not models that can be patched overnight. They were built on the foundational assumption that BZ has a value because in the entire observational history of space weather monitoring, BZ always had a value. The standard protective protocol for grid operators during an approaching severe storm is to reduce loading on the most vulnerable transformers, open certain transmission line segments to limit GIC path lengths, and have operations staff physically on site at critical substations ready to respond. This protocol requires advance notice, ideally several hours, minimally the 15 to 60 minutes that the Lagrange Point 1 Sentinel is designed to provide. The 15 to 60 minute window depends entirely on having a valid BZ reading at Lagrange Point 1. Without that reading, the cascade of model outputs that should have been flowing to grid operators since this morning, outputs that tell them this is a G5 event. Here is the predicted onset time. Here is the expected duration did not flow. The note that replaced the metal magnetometer models are now invalid. Grid operators are not operating blind in the absolute sense. They know a major event is coming. The G5 watch was issued. But knowing a G5 is coming without knowing its magnetic orientation, its likely reconnection behavior, or its expected duration is like knowing a flood is coming without knowing the predicted water level. You can sandbag? You cannot sandbag to an unknown height? Now add the condition of DSCO-VR itself. The Deep Space Climate Observatory was launched in February 2015, 11 years ago. Its design lifetime was 5 years, later extended through careful fuel and power management. It is currently operating beyond its planned operational end. The magnetometer instruments aboard DSCO-VR, the Fluxgate magnetometer, and the Vector Helium magnetometer have been accumulating radiation exposure and operational hours at Lagrange Point 1 for over a decade. Instrument calibration on aging hardware in the deep space radiation environment can drift. The question of whether the Null B-A-Z reading on May 26th represents a genuine physical property of the incoming CME or an artifact of sensor degradation on an 11-year-old instrument that was never supposed to still be running, that question has no clean answer yet. And the inability to answer it cleanly is itself part of the crisis. If DSCO-V R's magnetometer is drifting. The true BZ could be anything. Strongly southward, strongly northward, something in between. The instrument cannot be recalibrated from the ground on a 6-hour timeline. Its readings are what they are, and everyone downstream, every model, every forecaster, every grid operator is working with data whose reliability cannot be fully confirmed at the moment it matters most. The global coordination picture is no more reassuring. There is no unified international protocol for a null IMF plus G5 scenario, because no such scenario has occurred in the modern monitoring era. The Consultative Committee for Space Data Systems, the International Space Environment Service, the interagency frameworks that coordinate space weather response between the United States, European Union, Japan, and other spacefaring nations. All of these were designed around events that had BZ values. The response playbooks have never been written for an event that doesn't. Right now, in Boulder, in Darmstadt, in Tokyo, in separate national operations centers, teams are responding to the same incoming threat using different alert thresholds, different protective protocols, and different assessments of what the null BZ reading actually means. Some are treating it as a worst-case southward BZ equivalent maximum precautionary posture. Others are treating the sensor reading as suspect and waiting for more data before escalating. There is no common decision point, no shared operational picture, no moment at which the global infrastructure protection community acts as a single coordinated unit. Each grid, each satellite operator, each aviation authority is making its own judgment call, at its own pace, based on its own interpretation of data that the instruments responsible for generating it may or may not be measuring accurately. Now, before we talk about what could actually happen in the next few hours, I need to be honest with you about what science knows, what science does not know, and what we absolutely need to avoid getting wrong. Let me be direct with you for a moment, because this is where the story gets muddied by noise, and the noise, right now, is moving faster than the CME. Within hours of the G5 watch being issued this morning, the familiar machinery of misinformation had already started running. The same claims that surface after every major space weather event, recycled and amplified by people who either don't understand the physics or don't care to. Before we talk about what might actually happen in the next 24 hours, we need to clear the air. Not because the conspiracy theories are interesting, they aren't, but because believing them actively prevents people from understanding the real risk, which is serious enough without embellishment. The first claim circulating is that NOAA is hiding data, that the true severity of this event is being suppressed by government agencies coordinating a cover-up of some kind. This is wrong, and it is verifiably wrong in real time. Every measurement from the GOES satellite constellation, every X-ray flux reading, every particle count, every available magnetometer data point is published continuously and publicly at spaceweather.gov and through NOAA's Space Weather Prediction Center data portal. Not hours later, not after internal review, in near real time, the BZ readings from DSCOVR that are at the center of this story, public N, the G5 watch issuance with its handwritten note about model failure, public. The total electron content maps showing the ionospheric damage public through the NOAA, National Centers for Environmental Information, and through university ionospheric monitoring networks that operate entirely independently of any government agency. If no AAA were suppressing data, the dozens of independent research institutions, university space physics departments, and international monitoring agencies, the European Space Agency, JAXA, the British Geological Survey, the Finnish Meteorological Institute, that are all observing the same event with their own instruments, would be generating different numbers. They are not. The data is consistent across independent sources because the data is real and the sharing is open. The cover-up theory requires the simultaneous coordinated silence of hundreds of independent scientists across dozens of countries. That is not a conspiracy. That is not how science works on any continent. The second claim is that the High-Frequency Active Auroral Research Program, HAAEREP, is responsible for either causing or amplifying this event. The facility in Gakona, Alaska, operates at a maximum radiated power of approximately 3.6 megawatts. That is a meaningful amount of radio frequency energy for certain ionospheric heating experiments at very localized scales. It is also in relation to the energy budget of a coronal mass ejection, so vanishingly small as to be physically laughable. The CME, currently approaching Earth, carries kinetic energy in the range of 10 to the power of 24 joules, a number that, if you tried to match it with HAARP running at full power continuously, would require that facility to operate for approximately 10 billion years without interruption. The Sun has existed for 4.6 billion years. HAARP has existed since 1993. The arithmetic does not need a calculator. The third claim, and this one appears mostly in certain online communities that have been predicting solar catastrophe for years, is that the Sun is dying, dimming, or shutting down, and that this event is evidence of solar collapse. The opposite is true. A coronal mass ejection of this magnitude from a delta configuration active region at the peak of solar cycle 25 is precisely what a healthy, vigorous Sun at maximum activity looks like. The Sun is not shutting down. It is running at the top of its 11-year activity cycle, doing exactly what it has done at solar maximum for the approximately 4.5 billion years it has existed. The violence is normal. The scale is at the high end of normal. The Null IMF anomaly is unusual, but none of it signals a dying star. Clear those away. Now look at the actual limits, and they are real, and they matter. The most significant scientific limitation in this event is one that has been acknowledged openly in the research literature for years without being solved. There is currently no model capable of reliably predicting the BZ value of a CME before it reaches the Lagrange point, 1 sentinel. None. The magnetic field orientation of an erupting CME can be estimated based on the orientation of the source active region, the handedness of the coronal magnetic structure, and the known relationship between solar surface magnetic topology and eruption dynamics. But those estimates carry enormous uncertainty studies comparing predicted BZ at Lagrange point 1 to observe a BZ have shown that the correlation is weak enough that the prediction is barely better than chance for individual events. This is not a funding problem or a political problem. It is a fundamental physics problem. The magnetic flux rope that carries the CME can rotate, kink, interact with the ambient solar wind, and undergo internal reconnection during its transit through the heliosphere in ways that are not captured by current modeling frameworks. Null IMF and null helicity represent an even more extreme version of this problem. There are a handful of documented cases in the research literature, fewer than 20 across the entire satellite observation era, where incoming solar wind structures showed anomalously low or near zero helicity signatures. The physical mechanisms proposed to explain them vary: heliospheric current sheet crossings, interplanetary flux rope reconnection, compound CME interaction, instrument effects. Without a larger statistical base, without more case studies, without the observational data needed to distinguish between these mechanisms reliably, there is no framework for predicting how a null helicity structure will behave at the magnetopause. The models that exist were not built from null events. They cannot be extrapolated to null events with any scientific confidence. And then there is the question that sits underneath all of this: is the BZ actually null? Or is DSCOVR telling us something wrong. This is not a rhetorical question. The Deep Space Climate Observatory is 11 years old, operating 4 years past its design lifetime in a radiation environment that has been degrading its instruments continuously since launch. The Vector Helium Magnetometer and Fluxgate Magnetometer aboard DSCOVR have no in-flight calibration reference against a known magnetic field. Their calibration depends on ground-based checks performed periodically and on consistency checks with other instruments, but at Lagrange point 1, there is no other magnetometer to cross-check against in real time. The Advanced Composition Explorer ACE, which served as the primary Lagrange point 1 sentinel before DSCOVR, has been in an extended mission phase since 2005, and its magnetometer reliability has also been questioned in recent years. The honest scientific position this morning is this: the Null reading may be a genuine physical property of the incoming CME, or it may be a sensor artifact from an aging instrument at the end of its operational life, masking a strongly southward BZ that would, if known, produce a terrifying but at least modelable forecast. There is no way to determine which interpretation is correct before the CME's main body reaches Earth and the effects become directly observable. By then, the answer will be academic. One more variable that is not being discussed as much as it should be: the CME's arrival time carries a 2 to 4 hour uncertainty window in either direction. Solar wind conditions between here and the CME's current position can accelerate or decelerate the cloud relative to its estimated transit trajectory. It could arrive at the magnetopause earlier than the central estimate. It could arrive later. That window matters for grid operators who have been asked to implement protective measures and need to sustain elevated alert posture, a posture that has operational costs and cannot be maintained indefinitely at maximum intensity without consequences of its own. With that honesty on the table, let's look directly at the two scenarios that could play out in the next few hours, and neither of them is entirely harmless. Based on the historical record of G5 watch issuances, somewhere between 60 and 70% of maximum level geomagnetic storm alerts do not result in significant infrastructure damage. That is not a reassuring statistic so much as a contextualizing one. It means the warning system is appropriately conservative. It flags high-risk conditions even when those conditions don't ultimately produce worst-case outcomes. Because the cost of a missed warning is vastly greater than the cost of a false alarm. But it also means that most of the time, when we are standing here watching the countdown, the catastrophe does not arrive on schedule. The mechanism by which Scenario 1 plays out begins with DSCOVR. If the Null BZ reading is an instrument artifact, if the aging magnetometer aboard an 11-year-old satellite is misreporting a field that is actually pointing northward, then the CME approaching Earth carries a positively oriented BZ, north-pointing, Yarsh, parallel to Earth's own equatorial magnetic field rather than anti-parallel to it. When two magnetic fields point in the same direction and meet, they do not reconnect. They compress against each other, like identical poles of two magnets. The magnetopause moves inward under the ram pressure of the solar wind. There will be a sudden commencement signature, a sharp jump in ground magnetometer readings as the compressed solar wind hits, but the main phase of the storm, the phase driven by magnetic reconnection, does not develop, or it develops weakly, driven only by the partial southward components at the flanks and edges of the CMEE, where the field geometry is less clean. In this scenario, here is what you would actually observe over the next 12 to 24 hours. The bow shock arrives first, a sharp, rapid rise in the horizontal component of ground magnetometers, detectable globally within minutes. This is normal storm commencement and happens regardless of BZ orientation. Then, instead of the expected main phase, deepening. The disturbance storm time index, the DST index, which measures ring current intensification and is the primary real-time metric for storm severity, stays relatively flat. It might dip to -50 or -80 nanoteslas, which is a moderate storm. It does not plunge to the -200 or -300 nanoteslas range that characterizes a genuine extreme event. Aurora appears. Bright, widespread, visible at lower latitudes than usual because even a moderate storm produces equatorward expansion of the auroral oval. Photographers across Canada, Scandinavia, northern Russia, and northern Japan get the images they have been hoping for since the G5 watch was issued. At higher latitudes, GPS receivers show some positional drift errors of a few meters, degraded but functional. High-frequency radio over the poles experiences some blackout periods. Satellite operators deal with a modest increase in drag. Airlines reroute a handful of polar flights as a precaution. And then, over the following 6 to 12 hours, everything quiets. The KP index, the Planetary Geomagnetic Activity Index, peaks somewhere around 5 or 6. Maybe 7 at the storm's most active moment. The ionosphere, already stressed, takes another hit, but not an obliterating one. Recovery begins. The all clear is issued, probably sometime in the late hours of May 27th. Grid operators stand down from their elevated protective posture. The satellites adjust their orbits and resume normal operations. That is Scenario 1, and it is, statistically speaking, the more probable outcome of the two. But here is the uncomfortable truth that survives even this best case. The warning system failed, not partially completely. The primary operational forecasting model produced no usable output. The only G5 watch that exists right now was issued by a human being exercising judgment in the absence of model guidance, on the basis of a sensor reading that may or may not have been accurate. The world's early warning architecture for the most consequential space weather events was rendered non-functional by an anomalous BZ value on a 6-day-old CME from a solar maximum eruption. And this is solar cycle 25. There will be more eruptions. There will be more fast CMEs. The question of whether the Null reading was real or instrumental has to be answered, and the question of what to do when it happens again when the model legitimately fails and a human has to make the call alone, that question needs an institutional answer that does not currently exist. Even in the best outcome, there is significant work to be done, but if Null IMF is real, if this plasma cloud truly carries no magnetic field in the literal sense, then Scenario 2 is what we actually need to be worried about. If the Null BZ reading is real, if the plasma cloud now closing on Earth genuinely carries no coherent magnetic field, then the sequence that follows does not begin with a single catastrophic moment. It begins with something almost subtle, a tremor before the collapse. The first impact is not on a power grid. It is not on a satellite. It is on the magnetosphere itself, at the magnetopause boundary, where the solar wind meets Earth's magnetic field, and the difference between what happens here in Scenario 2 versus any previous G5 event is the difference between a controlled demolition and an unplanned building collapse. In a standard geomagnetic storm, reconnection at the magnetopause is driven by a coherent, sustained southward BZ. The field lines break and reconnect in an organized fashion, concentrated near the subsolar point, the nose of the magnetosphere facing the sun. Energy flows into the magnetosphere through a well-defined funnel. The ring current, the toroidal belt of energetic particles circling Earth at altitudes between roughly 2,000 and 60,000 kilometers, intensifies in a pattern that ground instruments can track in near real time. the disturbance storm time index drops, the auroral electrojet intensifies, and the system behaves badly but recognizably. Null IMF does none of that. Without a coherent field orientation to drive organized reconnection, the magnetopause encounters incoming plasma that exerts pressure but provides no magnetic coupling in a predictable direction. What likely results is stochastic reconnection spatially scattered, temporally irregular bursts of field line breaking across the entire magnetopause surface rather than concentrated at the nose. The radiation belts, the Van Allen belts, those concentric shells of trapped high-energy particles extending from roughly 1,000 to 60,000 kilometers altitude, receive energy injections from multiple directions simultaneously, in pulses with no predictable rhythm. The outer belt, already disturbed by the early May storm, responds not with the clean intensification pattern of a normal storm, but with chaotic flux variations particles accelerating in some regions, being lost in others. The entire belt structure oscillating without settling into any stable configuration. That chaotic energy loading in the radiation belts is the first punch. It is also the amplifier for everything that follows, because an unstable, over-energized radiation belt continuously dumps high-energy electrons into the upper atmosphere through a process called precipitation, and those precipitating electrons drive additional ionization in the ionosphere at altitudes between 60 and 100 kilometers, the D region, which is exactly where high-frequency radio signals are absorbed. More ionization in the D region means deeper, wider high-frequency radio blackouts. The ionosphere, already damaged from the early May storm, is being hit from two directions simultaneously from above by the incoming CME's direct energy input, and from below by the radiation belt, electrons raining down into it. This is the amplification factor that makes the pre-damaged ionosphere so consequential. Every effect that follows is not just additive to a healthy system's baseline, it is multiplicative on an already stressed one. The wounds from the early May storm become the pathways through which the new damage propagates faster and deeper. The first domino falls on global positioning and aviation. Instrument Landing Systems, ILS, are the ground-based radio guidance systems that allow commercial aircraft to execute precision approaches in low visibility. They operate in frequency bands between 108 and 112 megahertz. Their signals interact with the ionosphere indirectly, but the GPS receivers that modern aircraft use as primary navigation and as a complement or backup to ILS in many modern avionics architectures interact with it directly. Under severe ionospheric disturbance, GPS positional errors in the tens of meters range are not worst-case projections. They are documented outcomes from the October 2003 Halloween storms and the May 2024 event, both of which hit a healthier ionosphere than the one in place today. Tens of meters of GPS error in an aircraft on final approach is not a software glitch. It is a safety of flight issue. Aviation authorities in Canada, Iceland, the United Kingdom, Norway, and other high-latitude nations have established procedures for GPS-degraded operations, but those procedures involve delays, diversions, and restrictions on approach categories, meaning aircraft that would normally execute an automatic Category 3 approach in zero visibility must instead hold, divert to an alternate airport, or wait for conditions to improve. Multiply that across a global airspace system handling tens of thousands of flights simultaneously, with high-latitude routes heavily affected, and the ground stops and diversions accumulate into systemic disruption within hours of storm onset. Not all airports, not all flights, but enough to produce the kind of cascading delay propagation that air traffic networks, built around tight turnaround times and interconnected schedules, cannot absorb without widespread cancellations. Thousands of flights, not a projection, a conservative extrapolation from documented precedent, applied to worse ionospheric conditions. The second domino is in the ground, and it is already partially compromised. Canada's high-voltage transmission network runs across some of the world's most geomagnetically exposed geography. The Canadian Shield, the ancient Precambrian rock formation underlying most of central and eastern Canada, has exceptionally low electrical conductivity. Low conductivity geology means that when a changing geomagnetic field tries to drive GIC through the ground, the current is instead forced into the more conductive surface structures, the transmission lines. The physics is straightforward. Low ground conductivity concentrates geomagnetically induced current in metallic infrastructure rather than dissipating it through the earth. Canada, Scandinavia, and parts of Russia sit on exactly this kind of geology. They are, by the accident of their bedrock, the most electrically vulnerable regions on Earth during a severe geomagnetic storm. Hydro-Quebec's 1989 failure took approximately 90 seconds from the first GIC pulse to complete system collapse. The protective relays that were supposed to isolate damaged components instead triggered a cascade of automatic disconnections that took down the entire grid before operators could intervene. In the 36 years since that event, protection systems have been improved. Neutral blocking devices have been installed on some of the most vulnerable transformers. Operating procedures have been updated, but the fundamental geography has not changed. The transformer fleet has aged further, and the incoming CME, with its chaotic, irregular reconnection dynamics, will produce GIC waveforms that are less like the sustained unidirectional flow of a clean southward BZ storm, and more like a rapid series of irregular pulses, each one potentially tripping protective relays before operators can assess whether the trip was necessary or a false response to a transient. Transformer thermal failure under sustained GIC is measured in minutes to hours, not seconds. But relay misoperations, automatic disconnections triggered by anomalous current signatures that the relay interprets as a fault can cascade in seconds, exactly as they did in Quebec. The GIC waveform that a chaotic reconnection event produces may be precisely the kind of irregular, multi-frequency signal most likely to confuse protective relay logic that was designed and calibrated for normal fault current signatures. Scandinavia faces the same geology problem on a smaller geographic scale, but with a grid that serves populations heavily dependent on electrified infrastructure. Northern Russia has aging grid infrastructure with less sophisticated GIC protection than Western systems. The vulnerability is not uniform, but it is geographically concentrated in exactly the high-latitude regions that experience the worst storm effects. The third domino is overhead. Starlink currently operates more than 5,000 active satellites in low Earth orbit, predominantly at altitudes between 500 and 600 kilometers. OneWeb operates several hundred more. Amazon's Kuiper constellation was adding units throughout 2025 and 2026. Add national civil and military remote sensing satellites, weather satellites at higher low Earth orbit altitudes, and the total population of active satellites in the altitude band most exposed to thermospheric drag amplification during a major storm is well above 6,000 objects. During the May 2024 G5 event, SpaceX reported abnormal drag on multiple Starlink satellites and conducted unplanned orbital maintenance maneuvers on dozens of units. The thermospheric density increase during that storm was significant, but bounded. The storm was a single-phase event with clean reconnection dynamics and a defined main phase, followed by recovery. What a sustained, chaotic, multi-phase G5 event does to thermospheric density at 550 kilometers altitude over a 6+ hour period has not been operationally tested because it has not happened in the era of high-density, low Earth orbit satellite constellations. The orbital decay during such a period is not large in absolute terms, measured in hundreds of meters to a few kilometers for a multi-hour event, but the uncertainty in each individual satellite's actual position, compared to its cataloged predicted position, grows in proportion to the drag anomaly, conjunction avoidance. The process by which satellite operators and the U.S. Space Force's Space Surveillance Network identify close approaches and issue maneuver recommendations depends on position uncertainties, small enough that close approaches can be identified and assessed with meaningful confidence. When hundreds or thousands of objects simultaneously experience anomalous, poorly characterized drag, the position uncertainty ellipses for all of them expand simultaneously. The close approach detection system does not fail catastrophically. It becomes flooded with uncertain conjunctions that operators cannot confidently clear or act on. Because the orbital mechanics of every object in the affected altitude band are temporarily unknowable. Lost communication satellites mean gaps in internet coverage over oceans and polar regions. Lost weather satellites mean gaps in the observational data feeding the atmospheric models that aviation and emergency management depend on. The systems are redundant enough to survive individual losses, but not designed for simultaneous broad degradation across entire orbital altitude bands. The fourth domino requires no exotic physics. It requires only the loss of electrical power in a modern urban environment and the passage of 72 hours. Electrical power is not one utility among several. It is the substrate on which every other utility runs. Water treatment and pumping stations run on electricity. Cellular network base stations have battery backup measured in hours, not days. Internet exchange points and data centers have generator backup, but generators require fuel, and fuel supply chains require functioning logistics networks, which require functioning communications, which require power. Hospital systems have backup generation for critical systems, but not for every system, and not indefinitely. Financial transaction networks have redundancy built in layers, but those layers are not tested for multi-day regional grid outages in multiple countries simultaneously. 72 hours without grid power in a major city is not an inconvenience. It is the onset of a humanitarian emergency. Refrigerated medications. People dependent on powered medical equipment at home. Water pressure failing as pumping stations exhaust their backup capacity. Communication breakdown as cellular networks go dark sequentially as their battery reserves deplete. The infrastructure interdependencies that make modern urban life function smoothly become the pathways through which a single upstream failure grid power propagates into every downstream system that was never designed to operate independently. This is the cascade, not a metaphor. A documented failure mode that emergency management agencies have wargamed repeatedly and consistently identified as the scenario with the highest potential for large-scale civilian harm following a major geomagnetic event. And every step of this chain is amplified by the fact that the ionosphere going into this event was already torn. The pre-storm damage is not background noise. It is the crack in the foundation that makes the structure less able to absorb what is coming. Whatever scenario plays out, the most important thing right now is not predicting the future. It is knowing exactly which signals to watch, so we understand where we stand. I am not going to tell you what is going to happen. Nobody can. Anyone claiming certainty about the outcome of an event whose primary measured input is a null, a physical absence, is telling you something that is not grounded in what the data actually shows. What I can give you is something more useful than a prediction, a set of specific, observable, scientifically meaningful signals that will tell you, in real time, which direction this is actually going. 5 signals? Different timescales? Watch all of them. The first signal arrives in the next 24 hours, and it is the most important one because it resolves the central uncertainty that everything else depends on. When the main body of the CME reaches the DSCOVR satellite at Lagrange point 1, approximately 1 million 500,000 kilometers from Earth, the magnetometer will take its reading, and that reading will be published publicly in near real time at spaceweather.gov and through the NOAA Space Weather Prediction Center's data portal. What you are watching for is what BZ does at that moment, not the number before the CME arrives, the number when the dense, high-velocity plasma cloud itself crosses the satellite. If BZ remains null or begins oscillating chaotically, swinging between positive and negative values in rapid, irregular alternation without settling into a stable orientation, that is the signature of genuine structural null helicity in the CME body. And it significantly raises the probability of scenario 2 dynamics at the magnetopause. Chaotic oscillation is actually in some ways more dangerous than sustained southward BZ because it means the reconnection driving the storm is pulsed and irregular rather than continuous and predictable. If BZ abruptly snaps to a strongly negative value, negative 15 nanoteslas, or below, sustained, that means the earlier null reading was almost certainly instrumental, and you are now watching a conventional but severe southward BZ-driven storm develop. Damaging. Foreseeable. The models can run. Forecasters have a number. If BZ snaps to a strongly positive value, the storm's main phase will likely be moderate or absent. Scenario 1. The crisis de-escalates. The reading at Lagrange point 1 is the single most consequential data point of this entire event. Watch it live. The second signal runs from 24 to 48 hours from now and comes from the planetary KP index, the Global Geomagnetic Activity Index, derived from a worldwide network of ground-based magnetometers, updated every 3 hours by the GFZ German Research Center for Geosciences in Potsdam. KP runs from 0 to 9, with 9 being the highest level recorded. The threshold you are watching for is KP at or above 8, sustained for more than 3 consecutive 3-hour intervals, meaning 9 or more hours of near maximum geomagnetic disturbance. Why 9 hours specifically? Because the documented threshold for transformer thermal damage from GIC under sustained storm conditions based on the Quebec 1989 event, the analysis of the October 2003 Halloween storms, and subsequent laboratory and field studies suggests that the accumulated thermal stress on large high-voltage transformers becomes potentially irreversible after roughly 6 to 9 hours of sustained severe GIC loading. Below that threshold, the thermal load is serious, but the equipment can typically recover during storm recovery phases. Above it, you are in territory where the physical damage to transformer insulation may have crossed a point of no return regardless of what happens next. If KP stays below 7, the storm is major but manageable. If it hits 8 or 9 and stays there through 2 or 3 consecutive measurement intervals, you are watching the second signal confirm the infrastructure risk window is open. The third signal comes faster than most people expect, within 48 to 72 hours, and it comes from the aviation industry. Airlines and air traffic control authorities publish operational notices called NOTAMs notices to air missions that document GPS signal degradation, high-frequency radio blackout areas, and navigation system anomalies affecting flight operations. These notices are not classified. They are publicly accessible through aviation authority databases in the United States, Europe, and Canada. During the May 2024 G5 storm, NOAA's Space Weather Prediction Center recorded high-frequency radio blackouts covering most of the sunlit hemisphere, and aviation authorities issued GPS reliability warnings affecting polar and high-latitude routes within hours of storm onset. Watch for the volume and geographic spread of these notices. Isolated warnings over polar routes, which are always the first affected, indicate a significant but bounded event. Warnings spreading to mid-latitude transatlantic and transpacific routes, combined with reports of ILS, augmentation system failures, or GPS-guided approach restrictions at airports below 60 degrees north latitude, indicate that the ionospheric disturbance has reached the intensity and geographic extent of Scenario 2's first domino. This is your earliest real-world confirmation that the cascade has begun at the infrastructure level, not just at the sensor level. The fourth signal does not arrive for 1 to 2 weeks, and it requires patience, but it is the signal that will definitively answer the central scientific question of this event. Following any major CME event, the NOAA Space Weather Prediction Center, the IESA Space Weather Service, and research institutions including the Southwest Research Institute, the University of Michigan Space Physics Research Laboratory, and the Rutherford Appleton Laboratory publish post-event analysis reports that reconstruct the three-dimensional structure of the CME using data from multiple spacecraft, ground observatories, and heliospheric imagers. These analyses take time because they require careful cross-referencing of measurements from DSCOVR, GOES, the Solar Dynamics Observatory, the Solar and Heliospheric Observatory, and the stereo spacecraft to build a coherent picture of the CME's actual magnetic architecture at the time of impact. That post-event analysis will tell us whether the Null BZ reading was real, a genuine case of flux rope reconnection in interplanetary space producing a magnetically hollow CME, or an artifact of DSCOVR's aging magnetometer, misreporting a field that was actually there. This distinction matters enormously, not just for understanding this event, but for reforming the early warning system going forward. If the Null was real, the operational space weather community needs to develop protocols for Null IMF scenarios immediately, because Solar Cycle 25 has not finished producing extreme events. If the Null was instrumental, DSCOVR needs to be replaced urgently, not eventually, because the entire planetary early warning architecture currently depends on one aging satellite at Lagrange point 1 that has been running past its design life for 4 years. Either answer is important. Watch for the post-event report, probably published 2 to 4 weeks from now in journals including Space Weather, Geophysical Research Letters, and through NOAA's official event archive. It will be drier reading than this video. It will also be the most consequential document produced from this event. The fifth signal comes last 2 to 4 weeks out, and it comes from the electricity sector, which does not communicate in the same public language as weather agencies or aviation authorities. Power utility companies in North America, Scandinavia, and the United Kingdom do file reports with their regulatory bodies following significant operational anomalies. In the United States, the Federal Energy Regulatory Commission and the North American Electric Reliability Corporation collect reports of unusual GIC activity, transformer anomalies, and protective relay operations. These reports are typically made available to the public on a delay of several weeks to months. In Europe, the equivalent bodies, national energy regulators, and the European Network of Transmission System Operators for Electricity maintain similar reporting requirements. What you are watching for in this window is not headlines about blackouts. Those would be visible in news coverage long before regulatory filings. You are watching for the quieter signal reports of GIC-related transformer heating, unusual relay operations, equipment taken out of service for inspection following storm conditions. These are the indicators that the physical hardware absorbed stress that may not be immediately obvious in the public record. A transformer that ran hot during a storm but did not fail may have had its insulation lifetime reduced from 20 years to 5. That consequence will not appear in any headline. It will appear in a regulatory filing, eventually. Now, you have these signals. You know what to watch. Here is what to do with the time between now and when those signals resolve. If you do not have a 72-hour emergency kit, put one together. Not because collapse is imminent, it isn't. And I want to be clear about that. But because the gap between probably fine and grid down for several days is in a null IMFG5 scenario, narrower than it has ever been in the modern era, a 72-hour kit means water at least 4 liters per person per day, non-perishable food, a flashlight with fresh batteries, a portable battery bank for devices, and a battery-powered or hand-crank AM/FM radio. That last item is not nostalgic. It is the one communication channel that continues functioning when cellular networks fail and internet-dependent information services go dark. Local emergency broadcasts on AM frequencies will carry accurate information during a grid disruption faster than any platform that requires a functioning internet connection to reach you. Backup documents you cannot afford to lose identification. Financial records, medical information somewhere that does not depend on cloud access or a functioning cellular network. A USB drive in a drawer costs almost nothing. It becomes invaluable if cloud services are unreachable for 48 hours. During the event window itself, get your information from NOAA's official channels, your national meteorological or emergency management agency, and broadcast radio not from social media, where the signal-to-noise ratio during space weather events collapses almost immediately into a mix of accurate reporting, recycled misinformation, and straightforward panic amplification. The people who understand this best will be publishing through official channels and peer-reviewed rapid communications, not through engagement-optimized social feeds. And do not panic. That is not a platitude. Panic is a specific cognitive state that narrows your decision-making precisely when you need it to be wide. The preparation described above takes an afternoon. It does not require believing that civilization is ending. It requires the same calm pragmatism that leads sensible people to carry a spare tire you hope you never need it. You make sure you have it anyway, and having it does not keep you awake at night. Be ready, be informed, be watching. Whatever scenario plays out in the next 24 hours, you now understand exactly what is happening and why, and that understanding is not nothing. In a crisis driven by things that cannot be predicted, being the person who knows which signals matter is the most useful thing you can be. Thank you for staying through this. Genuinely, this was not light watching, and the fact that you made it here means something. Now I want to hear from you. Where are you right now as this unfolds? Have you noticed anything unusual these past few days? Aurora where it shouldn't be? Radio static? GPS? Acting strange? Or just that quiet feeling that something is off? Drop it in the comments. I read every single one. If you want to go deeper, how fragile the global power grid actually is, or what solar cycle 25 still has waiting for us before 2030, tell me below. I'll be back with confirmed data the moment the verification window closes. Because this story, it isn't finished yet. See you then.